Thank you very much. My name is Berend van Wachem. I'm from the University of Magdeburg, and I'm here with Fabien Evrard also, who's helped me in the last, or we've done it together over the last many years. So we work on multi-phase flows. So we have a turbulent flow, and we typically have a second or sometimes even third phase present in applications where we have either interfaces, we have, like in an ocean, we have droplets, or we have particles. And I think those are the three type of physics that we're interested in. And when I started with this, which is quite a while ago, in 2000, let's say, all the algorithms that you had for multi-phase flow were basically single-phase flow algorithms, and then you add in the steps for multi-phase flow. And that's something in the last, I don't know, 25 years or so we've tried to change. So just to repeat, and I think it really fits very well with the last talk, it's quite similar. You have the Navier-Stokes equation. So I wrote down the incompressible form, the continuity equation here, and the momentum equation, and how you typically solve this if you read classic literature, and you solve them for getting a guessed velocity field with guessed pressure. You solve a pressure correction equation, which is typically a Poisson type of equation. After that, you satisfy continuity, but not necessarily momentum, so you do a check if you have momentum is satisfied. If not, you redo and you start the process with better guesses. If this is satisfied, you have to update your source terms or everything that you've done explicit, volume fractions. Then you basically do that again, and if that's not the case, you have to iterate over this again, and once you've done with that, you update your time level. So that can be very expensive. And the problem also is that it typically requires unrelaxation if your guesses are not very good. And what's more problematic even, there's no guarantee that you find a solution. You could be iterating forever, and much of my PhD I was iterating forever. And it's typically because of large source terms or gradients that you have to deal with that exacerbate that. So I started looking at coupled solving, and there are a number of ways to do it. First of all, you could say, okay, we solve the velocity and the pressure together. There is no direct coupling, so we have a zero on the diagonal, but we have a really fancy solver. And there are people that do that, and that kind of works, but that's not been very successful for us. Secondly, we use artificial compressibility, which is also used in the single-phase flow community, where you introduce a coupling between velocity and pressure, but the coupling is such a way that it doesn't really interfere with the physics that you're interested in, which is hard because it means you need to find this artificial compressibility in such a way that it doesn't affect what you're looking at. And what we've looked at is there a way that we can write the pressure directly as a variable in the continuity equation? And that sounds a bit strange, and I'll try to illustrate that in a simple case. Fluid mechanics started in a staggered variable arrangement. As you can see that here, we have two cells, we have the pressure in the cell centers, we have the velocity that are staggered, and that works really well for a Cartesian mesh if the line between the pressure unknowns is exactly coinciding with where you store the velocity. If that's no longer the case, as in an unstructured grid, the advantage of staggered kind of go away. There are papers that do it, I've listed them here, Perot and Guericke, but it's very difficult to get it stable. So a collocated variable storage is much more, for finite volumes, much more natural for an arbitrary mesh element. But if you just implement this naively, you're going to get all kinds of problems between the pressure and the velocity are going to decouple. So what we adopted for what we call is called momentum-weighted-interpolation. And it was first introduced by the paper of Rhee and Chow, but they have just one single paragraph. They don't really say clearly what they do, but over the years, it's become more and more clear. And we've also done this now for multi-phase flow, and I'll try to sketch you the idea, that you get a general gist of the idea in the most simple equations possible. So there's the standard incompressible Navier-Stokes equations we have here. Here we have a cell, pressure and all the variables are at the center. The small f's are the phases, and here we have the cell phase between the current cell and the neighbor cell. So if we discretize that, here we have our first transient term, here we have our advection and diffusion terms. So A and B are the coefficients, and U and B is the velocity in the neighboring nodes. We do the same for pressure source terms, and this is the right-hand side term of the transient term. And our continuity equation is just that the sum of the fluxes at the faces add up to 0. We try to absorb the pressure and the source term into one. Just as the previous talk does the opposite, we try to absorb them into one. Our discretized equation then simplifies a little bit, where we just have this dp dx wiggle, which is our totally driving force of the flow. And this is basically an equation, a discretized equation for the velocity at the cell center of each of our cells. And after some simplifications, we can write an analogous equation. So basically we have here the averaged equations of the two nodal velocities. We average that to point E prime, where E prime is the point here which lies exactly between the cell and the neighboring cell in the middle. And we can write then, here we have the advection and diffusion terms. Here we have our driving force, pressure and source terms. And here we have the explicit right-hand side. And basically, if we write that out, so here we have that velocity at the cell face. We have the interpolation. We have here D and C are just coefficients. And what we have is we have the pressure gradient directly discretized at point E prime. And we have the pressure gradients from the cell P and E. P stands for the present and E stands for the east, so for the neighboring cell. And here we have some terms arising from the transient contribution. And then, of course, we have to do a corrector to go from E prime to point E, because in the end we need to evaluate it exactly at the cell face. So now we have an analogous expression, which is algebraic for the velocity at the cell face, which directly contains pressure. So if we use that velocity to close the continuity equation and discretize that, we have a dependency of pressure directly for our continuity equation. And we can use a more general solver for this. We don't need to know the velocity components at the cell face. We just need to know the net flux. So basically the velocity dotted with the normal of the face. And what you can show is that the pressure gradient difference between the small stencils, so the gradient at cell E prime and the two P and E, forms net a third order gradient, so it's a filter for pressure, so that pressure behaves well. We don't get a decoupling. So it's basically a filter which we apply inherently to the problem. So here you can see that equation again written out just in nu F, which is the flux at the face of each of the cells. So what we then solve, the governing equations we solve in a single equation system, which is very robust because we can make it as implicit as we want to. We don't need to under-relax. We don't need a very good initial guess. We've been doing this with PETSc since, I don't know, early 2000s, and it's been very successful. We typically use block-Jacobi and BCG stab, just as the previous talk. And what we solve then is the matrix here, where big A, B, C, D, E are our coefficients. And here we have the unknowns, the velocity field, the first three variables, the pressure field, and additional fields like energy, volume fraction, or there are a number of other fields depending on the exact problem that we're interested in. So what we do is we loop over the mesh, we gather all these coefficients, we put them into the matrix, then we solve it, and then we do that to the next time step. So I've been working with PETSc since about 2000. We're now in our third iteration. So our first MultiFlow was block structured with a static mesh. It was very implicit, one iteration per time step. We used multiple interconnected DMDAs. For each block, there was a separate DMDA and an MPI group working on them. We used PETSc binary file format, which we then converted to VTK to process with either scripts or look at with ParaView. We moved away with that because it's quite difficult to make block structured meshes for nice complex geometry, as well as we were interested in problems with many thousands of blocks, which becomes quite cumbersome to work with MPI, because if each of an MPI group, you have many MPI groups, MPI starts working much more complicated. So in 2010 or 11, we started with MultiFlow 2, which is basically a polyhedral mesh. We basically did everything in-house. We just used PETSc to solve the matrix. So we used the matrix and the vector object, but that's it. No DMs or nothing else. Partitioning we did with Parmetis, and we wrote our own HEF5 format to that, which we could directly use. And we were very interested in having a dynamic mesh, because most of our problems were required to be the mesh to be much finer in one region and for this to move around. And then we decided not so long ago to start with a third code based on this philosophy, MultiFlow 3, which is unstructured, can be block structured, can be polyhedral, and can be adaptive. And also to use the DMPlex framework, which we've been emailing a lot about. and adaptive mesh refinement based on the DMForest, PForest framework coupled with DMPlex. So I have a number of examples. I'm not sure if they work here. Let me have a quick look. Okay, I'll show them in the directory later. Or maybe I can do that now. It's where do I find the...
If you go to the left corner, if you push the mouse to the left corner,
yeah.
Go over there to
Here?
the far right. Just run over.
This one.
That one.
Yeah.
And then you can just double click it.
Yeah. So basically we have here a falling sphere. So we have a sphere in a fluid which is falling, which is one of the simple test case, but we know how that behaves. So that's why that's always been our test case. And we resolve the interface between the particle and the fluid in this case. We can do that for many particles, as you can see here. So we're resolving the flow around each of these particles. So we can do that for, I would say, 10,000, 50,000 particles, but then you already go into a mesh which contains 100 million cells. So it's going to be quite an appreciable numerical problem. Fabien worked a lot on sprays. So here you can see a spray. So here we have basically a chamber, and from the left here we're injecting liquid. And we're basically solving the Navier-Stokes equations and an equation which describes the interface. So we basically look at the spray, and the spray breaks up as it's going into the chamber. So again, the problem here is we would like to have a lot of mesh refinements where you have small ligaments, but outside of that here we don't really care. And with a static mesh, of course, you're paying the price for the whole geometry if you want to have a very fine resolution just around the interface. So that's made us work on, I think, yeah. So here you can see of our MultiFlow 3. So we basically have a sphere here. We have a flow going from left to right. Here you can see the processor number and the mesh. Here you can see the sphere and the flow colors. It's a periodic domain from left to right. We typically work with periodic domains at least in one direction, and you can see the mesh evolving around the sphere. And I think it's a von Karman type of street, so you'll probably see that the weight behind the sphere starts to oscillate, and the mesh refines nicely according to the vorticity in the flow behind that. And we can do that with many particles as well. So here you can see a box which is fully periodic. Here's a 2D cut of that box. We drive the flow by giving a pressure drop, and we're looking at what is the flow, the interstitial flow between these particles. We'd like to understand what is the drag on the particles, what's the drag distribution, and this kind of thing in the end of the day. Yeah, that's just to give you some flavor of the problems that we work on. Now back to my presentation. How do I get to full screen? View, enter full screen. Yeah. So these are some of the examples I showed you. So what we'd like to have is a coupled framework which solves various types of compressible and incompressible Navier-Stokes. We also do this for the compressible variations. Still pressure-based. It's designed for arbitrary domains where we can adapt the mesh where we would like it to based on specified criteria. And looking at particles, looking at droplets, looking at interfaces and its dynamics. For that we've used DMPlex, DMForest, PETSc, and the I/O routines for the mesh and the data. So for DMPlex what we do is we have what we call a coupled vector which contains all the coupled unknowns. So that is at minimum the 3 velocity components and the pressure. So it's the field number of fields is at least 4, but typically it will be more because we would like to also have the location of the dynamics of an interface would be a variable, where the interface of the particles are, etc. But at least it's 4. We also have many other vectors, like the volume fraction is not directly a variable we solve for, but we still have to have it as an unknown or as a known variable. So what we do is then we copy the DM, we reset the number of fields, and then we have a vector with those unknowns. If we want to have the mesh to refine dynamically, we couple DMPlex with DMForest using DMConvert. And we also use quite extensively still DMDA for what we call a particle mesh. So if you look at examples where we have particles and we want to know where particles are going to be colliding, we need to have some kind of geometric information where particles are. And for that, to have a Cartesian mesh makes it very efficient to find that out. So we also have a DMDA on top of the DMPlex itself. So we also spend quite some time finding the intersections, the geometric intersections between the DMPlex and the DMDA meshes. I think the biggest thing that challenges us is that we're not computer scientists. We are self-taught. I've been programming a long time, but very much try stuff, it doesn't work, we go back and try it again. And that makes it very hard to understand some of the details that go on in DMPlex. Also, we do a lot of our own discretization, as I tried to explain. So a lot of the frameworks are superfluous, but we still need to deal with them. Like we need to find a discretization object, which we don't really use, but we try to give it the options that it doesn't add computational time, but it still works for what we try to do. Some DMPlex implementations don't match our needs. For instance, the HGF5 output that you still have to go to a converter. So that's something we rewrote. We now have our HGF5 output directly from Plex, which we can read with ParaView or with our own scripts. How we create a geometry sometimes is not very compatible because we have, we can have 500 million unknowns and you can't call DMPlex create box mesh for that number of unknowns because we just run out of memory if we do that. We also had to implement some of our AMR-related routines, like computing and storing geometric mesh properties, where the mesh face is cut and you would still want to have the normals, the volume of a mesh. How we interpolate variables between coarse and fine meshes of some of the variables we implemented. Also how we handle hanging nodes, we call it. I'm not sure if that's a common thing, but where basically a coarser mesh and a finer mesh come together. How the fluxes are treated at hanging nodes. That's something which we also had to implement ourselves. We are still struggling with restart, which is really important because we run on large clusters where the maximum time is sometimes 6 or 8 or 12 hours. Our runs are typically days, maybe sometimes a week, and we need to do restarts, and that's been problematic. In fact, we don't have that working yet, so that's something we're still working on. And there's still some tiny bugs we find, which, like DMPlex PETSc with periodic meshes at the moment, which we hope we can resolve, or PETSc can resolve it. Yeah. So those are a number of challenges. And just to finalize my talk, we've published quite a bit in typically Journal of Computational Physics about things that we've been doing on the discretization and multiphase flow implementation with PETSc. And with that, I'd like to thank you for your attention.
Hello. Thank you very much, Berend. I'm talking with Matt about getting some of those bugs fixed while we're both here in town. Any other questions out in the audience?
Oh, that's a lot of great stuff. I just have one modeling question and then one solver question. So it wasn't easy for me to tell, but with the nozzle where you're spraying out, is the surface tension between the two fluids being modeled there? How
Definitely.
does that work? Okay,
So I think that's done with the VOF method.
Okay.
And we use the surface tension implementation with height functions and the Bragg-Mill type
so
model
you have
for surface
you kind of
tension,
calculate
CSF.
some curvature between.
Correct. We have to calculate the curvature with
Okay.
height functions. Yes, we do that.
Okay,
Yes.
very cool.
Yes.
Okay, and then can you go back to your large matrix?
Yeah.
So one thing it looks like you could do, I don't know if you're doing it now, but it looks like you can field split A, B, C, D, and E and do it multiplicatively, and that will solve it exactly because it's block tridiagonal. So you would invert A, B, C, D, and then invert E, H separately. Did you guys try that, or?
No, I think that we have 4 zeros here is not very common. Typically, maybe not in this case, there will be some non-zero here. For instance, if the velocity would depend on the temperature.
Okay.
So the density would depend on temperature, then we would get non-zeros here.
So depending on what your rheology
Exactly.
is. Oh, okay.
It will change the layout of the matrix.
And did you ever consider trying out one of the patch solvers? Because, in the simplest case, we can think of it like Vanka, where you have these constraint nodes in the middle of the cells, and you would solve the little cell problem as a preconditioner. And we have that implemented. We should be able to try it just with options and see whether it's effective. I've never seen it for multi-phase, but we have a lot of single-phase stuff where it works pretty well.
We've never tried it, so that'd
Yeah.
be great, yeah.
Cool, thanks.
Other questions? All right. Well, if not, let's thank Berend one more time.
Thank you.